The last recording I'll just discard. Anyway, welcome back, everyone. Today we're going to look at the rest of the matrix stuff. We did the partial fractions, that's matrix stuff. And today we're going to look a little closer at the matrix stuff. Now, I'm going to do the matrix information here with some applications that you're going to be seeing in linear algebra. Okay, so a little bit of this, like the characteristic polynomials, that's not in the scope of the course. Everything else is. But the characteristic polynomial makes for a really nice example for us doing linear combinations of matrices. So I'm going to do that. And it provides a nice little segue for working with inverse matrices as well. So here we go, guys. We're going to be talking about matrix multiplication. And however you managed to do matrix multiplication before, I'm going to express it in terms of a row on the left dot a column on the right for the dot product of vectors. Well, I'm going to consider the rows and the columns of matrices to be vectors now. And we'll take dot products to do the matrix multiplication. I'm also going to be looking at determinants, which you've heard of, and traces, which you might not have heard of, but traces are very simple. We have what's called the principal diagonal. That's the forward diagonal. Sometimes you start at the top left and you just run down to the bottom, just looking straight along that diagonal. Add everything in there, that's called the trace. Then we're going to talk about inverse and identity matrices and talking about how to solve matrix equations using those inverse and identity matrices. I'm still looking for 2 people to show up and getting people kind of coming in and out. I'm not even sure I get the whole list here. Yes, there's my whole list. Okay. I'm especially looking to see Joanne show up because I got her on the list for laptop today. She should have gotten an email from that anyway. Okay. There we are. Okay, guys. Now here's like the stuff I'm going to put on the side to give us an idea of where we're at on this. Okay. Yes. Oh, look at the lag on that. Look over here, guys. All right. So when I'm talking about matrix multiplication, I'm talking about 2 matrices A and B that multiply up to a matrix C. The matrix C has rows, which I'll index with the letter I, and columns that I'll index with the letter J. So I'll have row I on the left and column J on the right. And if I take their dot product, I'll get the entry for row I, column J in the product matrix C. And that's how that'll work. Now, you have been introduced to matrix multiplication by a column vector with variables in it, and you've introduced to that as solving systems of equations. But in linear algebra, that's just how you get kind of motivated to actually do the linear algebra, this solving system of equations. People that are doing linear algebra, they see that matrix multiplication as a transformation. It sends one point, XYZ, to another point, XYZ, either in 3 space or 2 space or however many dimensions you're going to be working with. And sometimes that matrix multiplication is equivalent to just scaling the original vector. And that's a very interesting thing to happen on a matrix transformation. And so we want to look at things like that. And so we assume that there's some scale factor lambda hanging around. And we use the theory of determinants to know that if there is such a thing, so that if I multiply a vector xyz, that's what I'm writing as x, that's the vector xyz, by matrix A, and I've just ended up scaling it, just making it bigger or smaller, I know that means the determinant of A minus lambda I is 0. And what's interesting about that is that gives me a polynomial in lambda, and that polynomial in lambda can be solved. And you can find the two or three or however many lambdas that solve it, depending on whether you're looking at 2 by 2s or 3 by 3s. And what's really interesting is you end up with a polynomial in lambda that if you plug in a into it, yeah, you end up with a polynomial that you plug in the matrix and it evaluates to 0. So the matrix, you found a polynomial that has a matrix as one of its roots, which is really cool. And that polynomial that has a matrix as one of its roots is called a characteristic polynomial. You're not going to have to know how to do that. Are you going to use 3 to 3 matrix to solve simultaneous equations? Yes, yes, but only in matrix form, Joel. And the ones that we're going to do on those, we're going to use the inverse matrix method on that. That's the only one I'm really interested in, is the inverse matrix method. The 2 by 2s, I'll make you form the 3 by 3s. Don't worry, because I'll give you the inverse matrix. Okay? Yeah. The 2 by 2s, yeah, you got to calculate the inverse. But calculating the inverse on a 2 by 2 is wicked simple, and you'll see that in the others. Now, the inverse matrix is any matrix that times the original matrix gives you the identity matrix, where the identity matrix is just the ones along the diagonals and zeros everywhere else. Okay? And the cool thing is, if you got an equation in the form ax equals b, where x is x, y, z, and b is bx, by, bz, then you can just solve for x by multiplying both sides by the inverse matrix. Cancels on the left and multiplies on the right to the solution. That's all there is to it. Okay, so let's dig right in. Now, I gave you too much information here. Okay, we're going to say always matrix multiplication is always a dot product of rows and columns. Okay, let's look right here. Everybody's fingers in the chat box. I have 17 students in here. Okay, and me and my clone makes 19. Okay, so here on the side right there, I want you to see rows on the left. That's the important thing. When you're looking at the left matrix, you're always looking at rows. On the right, you're always looking at columns. Okay? So my first question is, how many rows are there in my matrix A? A is always my first matrix. How many rows in my first matrix A? This is A. How many rows, guys? Thank you. Awesome, 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 awesome. So this is known as a 2 by, well, how many columns in that first matrix, in the matrix A? 3, 3, 3, 3, 1, 2. So this is called a 2 by 3 matrix. Okay? Now, this is a little trickier, but you'll see it. Okay? How many rows in matrix B? That's right, Danny. Rows in matrix B. Everybody, tell me. Danny's right. He's right. Yeah, I'm right here. Row, row, row. There's 3 of them, right? Okay. And now, how many columns in matrix B? Yeah, the shape is 3 by 1. That's true. Yeah, everybody sees that? Thank you, Winter. Thank you, Jada. Now, Jada, I heard, I talked to Nikki again. Yes, and she tells me that you're in the process right now, so something's happening for you. I need an eye out to see if Jan because I've got her. Yeah, you're in the process for home delivery, and that's cool. Thank you for letting me know about that, and I hope we can be taken care of. I've got a laptop for Joanne. I want to make sure that she's up today because it's a pickup day. Okay. I hurried fast yesterday and got 2 students' laptops. Got 2 of my students on the list for today. Okay, and I got you And that's kind of everybody. That's kind of everybody. Okay. Here we are. That's cool. 3 by 1. I'm looking still for one. I'm looking for Joanne and one other student I speak to privately. I've got a process of a submission for 6 o'clock. My hold out. Okay. So here now I'm gonna erase the answers. But I made this one really easy to be able to tell me what it is. The entries in A row 1, that's row 1 of matrix A. What are the entries in row 1? That's right, winner. Everybody else, everybody sees it? Everybody sees it? Thank you, Alice. That's 2. I got up to 18, 3. Sam, 4. That's Casey. Thank you, Casey. 4. I'm missing 14. Thank you, Jada. 5. Missing 13. Danny, 6. Milady, 7. Okay, thank you. 8. Vicky, thank you. I'm still missing, most. I got 10 students who aren't in the chat box. I need you in the chat box. I need everybody in the chat box today. Okay, because we're doing matrices, and I need to know that you're with me. Thank you, Elizabeth. Oh, I found your letter, by the way. I found the letter that you gave me. Okay, so you don't have to try to find that for me. I asked you for that in email before. That's okay. Okay, and I've lost my count now. Oh, and I've got a bunch of students who aren't joining in. I'm so afraid you guys aren't going to be following this if you're not following in. Okay. Okay, I got to go on. Okay, yeah, the entries are 1, 1, 1. And rather than looking at that as a column now I'm going to look at it as a vector. 1, 1, 1. Okay? Now, what are the entries in B column 1? As if there was another column. What are the entries in B column 1? Everybody? See if I can get a few answers in there. What's B column 1, guys? Thank you, Winter. Thank you, Sim. Thank you, Danny. Yeah, 1, 2, 3. So I'm going to enter those in there, 1, 2, 3. And now I'm going to form the dot product. Okay? Now I'm going to create the dot product. We've done this before. Who can tell me what the dot product is? Who can tell me what the dot product is? Somebody tell me what the dot product is on these two vectors. And the answer is not 1, 2, 3, but you're close. I'm not sure what that thing is, the colon whatever, but that's not it. Okay, what's the dot product, guys? What's the dot product? Hint, the answer is not a vector. No, not that would be the sum of the twos. I'm looking for a dot product, Caitlin. Winter gets the prize. Showing once again why she is like one of my favorite students this term. Felix got the answer too. Now, who sees how they got there? Because you saw the 1, 2, and 3, that's no problem. I said dot product, you said product, oh, that means multiply. Yes, but don't leave it as a vector where the commas are become plus signs. And so there is your dot product, 6. Okay? And that's going to go over here as part of my answer on the product. 6. Okay? And now, let's do, what's row 2 here? What's row 2? A row 2. A row 2? That's right, 1, 2, 3. Oh my. What just happened? Oh, guys, what is B column 1? What is B column 1? And I got myself confused. I was looking too much in the chat. What is B column 1 actually? What is B column 1? That's the right-hand matrix. What's that column? What are the entries in that? Yes, 3, 2, 1. And I don't even know if you guys told me that or not, and I can't scroll up in the chat, can I? Yes, I can. And what were the answers that I got? B column 1, 111. Okay, and yeah, people were giving me the answers to row A. No, it's 321. Everybody sees 321? You said 321, and yeah, and then you got confused because, like I was saying, I was kind of going along with it, right? Because the thing is, I can't see the matrix because you can see it up there, but I'm zoomed in on my laptop to make it on my tablet to make it visible, and so I just kind of went with you guys. Okay, so here we go. In any case, the dot product doesn't change. It's still 3 plus 2 plus 1 is 6. Okay? And now, A row 2 is 1, 2, 3. B column 1 stays the same. 3, 2, 1. Now, what's the dot product, guys? Everyone give me the dot product. I got 18 students. I want to see 18 answers on this. 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, missing 8, 11, 12, missing 6, lost 1. Oh, but she already answered. 6. I'm missing 6 students who just aren't in here, who aren't helping me out. I can't even tell who they are. I can't like follow along to see who it is. Okay, so yeah, it's 3 plus 4 plus 3 is 10. So there's the important thing, guys. And we get 10. Now, guys, how many rows in matrix C? That's the answer matrix. How many rows in matrix C? 2. People see 2. How many columns in matrix C? 1. How many entries is that? That's 2 total entries, right? Yeah, thanks guys. That's a total of 2 total entries, right? And you end up with 2 entries because I had the dot product of 2 rows and 1 column. If I had 3 rows and 4 columns, I'd have 12 dot products and 12 entries. And that's how we end up with this. We always end up, let me give myself a little bit more space here, okay? The shape of the matrix is always given by the outers. The outers, 2 by 1. And that gives me the shape. That's called the outers. The inners have to match. And the reason the inners have to match is because you're making dot products. And you can't make dot products if I'm like missing something, right? I mean, what would it mean if I was looking at this thing and it was just kind of missing an entry? I'm kind of like, oh, what's going to happen here? That's not going to work. So we have to make sure that we have exactly the same number of columns on the left as we have rows on the right. And the answer is going to be the number of rows times the number of columns in a matrix. So we get a 2 by 3 by 3 by 1, end up with a 2 by 1, and there's the entry, okay? So let's do one more of those, okay? I started this one up already. Okay, let me get this zoomed as much as I can while still giving myself room for everything I need. Is that going to work? I think so. Okay, that's as much space I can do. Now on this one, I've listed what A row 1 is and what B column 1 is. Everybody sees we got 2 rows, 2 columns, and everything. Yeah? Okay. So let's just get them all set up and then we'll do the dot products, okay? What's A row 1? What is A row 1, guys? I'm looking at the entry for C12. So I'm looking at row 1 on the left. What's A row 1? 3, negative 2? 3, negative 2? Okay, so you're seeing it. Good. Okay. What's B column 2? B column 2. That is row, 5, 1 is row 2 of column A. That's A row 2. And somebody tell me what, and I'm seeing a couple of answers. I see one answer is right. Danny's right. Okay. So B column 2, look at the matrix B. This is, I'm calling matrix A. This I'm calling matrix B. It's always first is A, second is B. Here's column 1. Here's column 2. Okay. So the entries in B column 2 are 2, 3. Okay. Yeah, I know. And this is, like you got to get your eye working right for this to happen. And that's why I'm kind of like making sure that people get a chance to come along with me. Okay? Yeah. Now, because and that's something you want to train your eye on. The left-hand matrix, all you want to see are rows. And the right-hand matrix, all you want to see is columns. So when I'm looking here, I always see rows over here. Whoop. With a pointer, not a line. I always see rows when I'm looking over here. Over here, I just see columns. Rows on the left, columns on the right, rows, dot, columns. Okay, and that's how this is going to work. Now, what's A row 2? A row 2. That's right. That's right. Yeah, and it's 5, 1. That's how it's going to work. Yeah. 5, 1. Okay. What's B column 1? 1, negative 5. Now, let's finish this up. What's A row 2? A row 2. 5, 1, yeah. And what's B column 2? B column 2. That's right, Danny. Thank you, Alex. Yeah, 2, 3. There we go. Okay, so we're ready to rock and roll here. Let's start doing some dot products. What's the dot product that gives me C11? What's the dot product for C11? Okay, not quite, Danny. Try again. That's right, Alex. Yes, that's right. Thank you. Thank you. Get the fix, Danny. That's good. Don't be sorry. This is how we learn. Okay, that's all great. Yeah. You want to be sorry? Be sorry about the misspellings. Sorry. That's your English teacher's problem. Mistakes in math class is how we learn. Yeah. So 3 times 1 is 3. Negative 2 times negative 5 is 10. And we add those and we get 13. Now let's move over to C12. This dot product. What's the dot product now, guys? 0? Oh, that's cool. 6 plus negative 6. Okay. What's the dot product over here? Sorry. And this is going to be row 2, column 1. C21. And wow, that's weird. And how about C22? How about C22? 13. I got 13 again? I got 13. That's like weird. It's like, I ended up with a diagonal matrix on this. 1, 1 was 13. 1, 2 was 0. 2, 1 was 0. And 2, 2 was 13. It's like 13 times the identity matrix. Yeah. That's like 13 times the identity matrix. Wow, that's wild how that happens. Yeah, that's 13 times the identity matrix. You know what? normally if I see two matrices that multiply up to the identity matrix, I think of them inverses, right? But these don't quite multiply up to the identity matrix, right? It's off by a factor of 13. You know what I think? I think this is almost an inverse. And if I had just divided everything in this original matrix, B by 13, I would have ended up with the identity mix. And that would have meant that this and this were inverses. Making my examples work for me. Yeah, we'll talk about that a little bit more as we go along. Okay, I'm going to do a little bit of a flat over here for an example from linear algebra. Okay, guys? Yeah. Now, here we go. Let's take a look at that. Okay, there's that same matrix A we've been looking at before. That's 3, negative 2, 5, 1. Okay, now, we know the row 1 and row 2 and column 1 and column 2 are on this thing. That's not cool. Okay. Now, there's two things I want to pull off of this thing. One's called the trace, and you love trace. Trace is so easy and cool. And it's not from a row or a column. It's from the principal diagonal. And it's a plus thing. It's a plus thing. Okay. And for the trace, I'm just add the elements in the principal diagonal. If I add the elements on the principal diagonal, what do I get? If I add the elements in the principal diagonal, I get. That's right. And it's called the trace. That's called the trace. Okay? Now, analogously, this is kind of like adding the roots of a polynomial. And you end up with a trace on that. Okay? Now, I want to know what the determinant of this matrix is. Who knows how to calculate determinant on a 2 by 2? It has to do with the diagonal as well, but it has to do with multiplication. And it has to do with 2 multiplications. Anybody know what the determinant is on this? Anybody calculate the determinant on this? What is it? Hint. Hint. Look at the chat box. Look up above the 4. What number do you see? Determinant is 13. And you get that by multiplying the principal diagonal 3 times 1 and then subtracting the product on the back diagonal. And so that works as 3 times 1 minus negative 2 times 5, and that's going to be 13. Now, this is analogous to the product of the roots for a polynomial. And if I know the sum of the roots for a polynomial and what the product of the roots is for a polynomial, I can create a polynomial out of that, where I write x squared minus the trace plus the norm, the product. And here what I'm doing is I'm writing x squared minus the trace plus the norm. I'm giving myself a little more real estate on this so I can write this. These two together allow me to write a polynomial. That polynomial, I need to clean this up. I need just a little bit more room. Minus 5, 2 times 5. And from these, I'll go x squared minus 4x plus 13. That's x squared minus the trace plus the determinant. And this is called characteristic polynomial. I'm going to leave this obvious. And I'm going to show you another way to calculate this. First of all, I want to remind you guys, for any two matrix, how you calculate the determinant. You've got two diagonals for the diagonal. The principal diagonal, which I sometimes call the forward diagonal, and the back diagonal. And what you do is you multiply on the principal diagonal, AD, then subtract along the diagonal, BC. And that's how this works. Now, let's look at this matrix, my A minus lambda off matrix. Okay, if I had lambda I here, that just means lambda times the identity matrix. And yeah, it's called that the L in Greek. And it's lambda used for things called eigenvalues in linear algebra, and you'll see it used for wavelength in physics. Okay, they like it for wavelength in physics. Okay, and where nu looks kind of like a V is used as frequency, so you get speed as wavelength times frequency. Lambda nu, V equals lambda nu is one of those basic physics equations. All right, so now let's go ahead and let's calculate the determinant of this matrix A minus lambda I. Okay, so let me give myself just enough real estate to do this. I'm going to calculate the determinant of A minus lambda I. For determinants on a matrix, we use absolute value bars. Okay, and this is going to be now 3 minus lambda times 1 minus lambda minus negative 2 times 5. Okay, so that's plus 10 over here. And over here it's going to be 3 minus 1 lambda minus 3 lambda is minus 4 lambda. And then plus lambda squared. And when I clean that up, I get lambda squared. Lambda squared minus 4 lambda plus 13. In other words, yeah. Let me clean that up just a little bit more for the notes. And that should look a lot like the matrix we got using trace and norm, because that's what happened. Okay? Yeah. And I'm going to write that again to free up some space. For everything else I'm going to do today. All right. Now, my claim is that that is now a polynomial that has the matrix A as a root. Now, to turn that into, and so we're going to calculate it. We're going to calculate it. Okay? And so to calculate this, I'm going to have to figure out what A squared is. I'm going to need A squared. I'm going to need minus 4 times A and plus 13, but 13 is a number. And I need matrices. If I'm adding things to matrices, I need a number. And so I will turn this into 13i. So I'm going to calculate A squared and negative 4A and 13i, and then I'm going to add those all up together, and I'm going to claim that I'm going to end up with a zero matrix when I'm done. Okay? So let's do that. Now, let's start off finding A squared. For A squared, remember We're talking about row, column, rows dot columns. Okay, and that's how you want to see it. Okay, so what's the first row dot the first column? What's the first row dot the first column? Anybody? I'll write it down if we need to. That's 3, -2, dot 3, 5. What's that? Anybody? What's that? Am I there or not? What's the dot product there, guys? First row, first column. What is it? Everybody stopped. Can you hear me? Nobody's answering. Can you hear me? Hands up, you can hear me. Yes, okay, that's good enough. That's good. Okay, you can lower your hands, that's fine. We're doing the dot product, the same thing we just did, guys. I want to know what the dot product of row 1 and column 1 is here. That's right, Jada, thank you. 9 minus 10, and that's going to be -1. Okay? Good. And now let's calculate some more. Calculate some more, okay? First row times the second column. Times the second column. And when I say row, I mean the left, and when I say column, I mean the right. Okay? Yeah. So, what's the dot product this time? 3, -2, -2, 1. What's the dot product now? I know Jada can figure it out, but the rest of you guys can too, right? Alex says it's -8. I say it's -6 plus -2. And I think Jada and Alex are right. And so that's the first row, second column, -8. I'm constructing it here on the right, okay? Now I want to calculate the two missing entries here, the second row entries. And so for those, I'll need to start with the second row. What's the second row? And obviously I mean on the left. What's the second row? Second row is what? Somebody tell me. Just type the numbers. Somebody tell me. What's the second row on the left? What's the second row? This matrix. What's the second row? Thank you, guys. And now this matrix. What's the first column? First column. First column over here. 3, 5. Thank you, guys. 3, 5. What's the dot product? What's the dot product? 20, 15 plus 5. That's 20. That fills in one of my holes. Now, I'm still working with the second row, so I'll keep the second row up there. But now, what's the second column on the right? What's the second column on the right? Not sure where the... That's right, -2, 1. Thank you, Sim. Thank you, Alex. What's the dot product now? What's the dot product? That's right, Alex. And I'll just fill it in over here now. So this is a squared. Okay? Now I want to find negative 4a. And this is scalar multiplication times a matrix. And it works just the same as scalar multiplication times a vector. Multiply everything in sight by negative 4. Okay? So this is going to give me negative 4 times 3, and negative 4 times 5, and negative 4 times negative 2, and negative 4 times 1. So negative 4a is going to be, what's my m numbers here? Negative 4 times 3 is negative 12. Watch my arithmetic, guys. 8. Yes. And then what? Negative 20. Yeah. And then negative 4, right? Okay. And now 13i, I think we can just write down, huh? What's 13 times 1? 13 times 0. 13 times 0. 13 times 1. There we go. Ooh. That was a weird place to finish that. There we go. Okay, now, to find the sum of these, I can do it one piece at a time, or I can do it all at once. If I want to do it one piece at a time, I'll find a squared minus 4a first. And that, for matrix addition, it's none of this dot product stuff right there. Addition is real simple, just entry by entry. What's negative 1 plus negative 12? Negative 1 plus negative 12. That's right. So I could start with negative 13. And then negative 8 plus 8. Negative 8 plus 8. Yeah. Okay, then 20 plus negative 20. Yeah. And then negative 9 plus negative 4. Yeah. Okay. And now if I add that, to my, yep, all zeros. Guys, this is the 0 matrix. It kind of goes along with the 1 matrix, the identity. That's the 0 matrix. And what I just found is that a squared minus 4a plus 13i is 0. So we just found that you can plug a matrix into a polynomial and find that it's a root. Wild. You'll have heard me say before, degree 2 polynomial has 2 solutions, right? Well, yeah, when I bring it up to matrices, though, there's an infinite number of solutions. Because there's lots of ways to get a matrix that makes this happen. But in any case, so this was an exercise not so much in finding and working with a characteristic polynomial as in just matrix multiplication and matrix addition and linear combinations of matrices. That also had a nice little spot here. The idea here was, sometimes it's possible to actually get stretches off of this, because these are transformations. That 3, negative 2, 5, 1, you think of that, oh, that's what I get when I have a matrix 3x minus 2y and 5x plus y. And so I bust that up as 3, negative 2, 5, 1. I grab that matrix of coefficients. Okay? And the real thing is that's a transformation. It takes a vector x, y, and it sends it to a new place. It takes that xy vector, and places it somewhere else. So it takes a point in space, in 2 space, and sends it to another point in 2 space. In the process, it does 2 things. It changes the length, the distance from the origin, and it also twists it some. kind of change the angle from the origin. Now, this idea is, for the lambdas, is you want to find a particular direction where it's all scale factor, all stretch, no twist. And that can be done if you let me bring things into complex numbers. But sometimes it can be done just straightforwardly as well. And when you can get that, what you have right there is something which is kind of equivalent to diagonalizing the matrix. That's doing a transformation on the original matrix that gets rid of these entries, turns those into zeros. Okay? And what's interesting that is that scale factor is actually a root of the original polynomial, of that original characteristic polynomial. So in fact, this one doesn't have, this one right here, you see that x squared minus 4x plus 13? That was my characteristic polynomial. It's got complex roots, and the complex roots are 2 plus 3i and 2 minus 3i. Okay? And that's the scale factor. And that scale factor is called an eigenvalue. And the vector that you apply it to is called an eigenvector. It's the special direction that gets just stretched. But it doesn't get stretched by a real amount, it just means by a complex amount. In this example. There are other examples that get stretched by a real amount. And that just has to do with the discriminant of the characteristic polynomial. All right, that's enough for that one. So let's do more fun stuff. Now, next thing I'm going to look at is calculating determinants. Here is why I want to calculate determinants. I calculate determinants because it's actually a closed form for the inverse matrix that involves dividing by that determinant. You'll have seen other things you can do with determinants, and that's fine too. I'm not going to be able to go into all the details on that because we're missing a lecture on this. So I'm just cutting to the chase on this. Matrix multiplication, determinants, inverse matrices, and then we'll be there. Okay? Yeah. Now, and you'll see that reflected, just those kind of questions on our exam for this material. That's the stuff I want you to take with you into linear algebra. Okay, so here's the idea. We're going to expand off of a row, or we're going to expand off of a column. Now, in the normal course of events, when people are going to calculate the determinant, the first thing they do is they just expand off of row 1, because that's the easiest thing to happen. Now, to expand off of row 1, what I'm going to do is I'm going to take the entries in row 1. What are the entries in row 1, guys? What are the entries in row 1? Anybody? Tell me what the entries in row 1 are. 3, negative 2, 1. 3, negative 2, 1. Yeah, that was the column 1, Sam. 3, negative 2, 1 is the row. There you go. Remember, columns are like in front of a building. Yeah? Columns are like in front of a building. I know sometimes students get confused with what's a row and what's a column. Columns are like front in a building. They go up and down. Yeah? Okay. Rows are the other thing coming across. So 3, negative 2, 1. And here I'm going to write these entries, but I'm going to write them spread out. Okay? And that's what people do when they're calculating these. Now, what I'm going to multiply them by, each of these entries. Now, there's one other thing I need to do. I need to change a sign. I need to change the sign. And this sign I'm going to change. Okay? In general, when I'm expanding, these are the ones whose sign I'd have to change if I was expanding it. That's called a checkerboard. And those entries, if you're expanding, when you're expanding off of that row or that column, those one have to have a sign change in them. What's special about those positions is the sum of the column and number and the row number is odd. For example, guys, this right here, this entry is in which row? Which row is this entry in? Which row is this entry in? Somebody? 2, yeah. Which column is this entry in? Which column is this entry? 2 plus 1 is 3. That's odd. So what's actually happening here is we're going to change the sign. If like -1 to the power, row number plus column number, that's how it's going to work. And so we have, this is 1, 1. Row 1, 1, that's even. Every time I move 1 over 1 in rows or down 1 in columns, I'm going to change sign. So I go positive, negative, 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 positive. Or you could just remember the checkerboard. That works. Okay? So in any case, I had to change the sign on negative on 2. Now here's the fun thing. Why did I leave all that extra space? I left that space because now I need to calculate minors. Now minors are the determinants of the reduced matrices. That 3 that I started with was in the 1, 1 position, yeah? That's a 1, 1 position. Okay? This was the 1, 1 position. Look in the 1, 1 position, and I'm going to get rid of, because I'm looking at the 1, 1 position, I've already got that. That's my representative here. 3, like this, okay? What's left when I get rid of that first row and the first column? What's left when I get rid of the first row and the first column? First row is gone. First column is gone. I end up with 1, -4, 2, 7. I'm not changing this now. I'm not changing that. Just undo just what I just did. Yeah. And so that's what I'm going to place in here into this reduced matrix, this punctured matrix. 1, -4, 2, 7. Okay? And now I'm going to do that for all the other entries too. The -2 that I had to change the sign on is going to have a minor associated with it. And the 1, because there's no sign change, I'm going to have a 1 on that. It's going to have a reduced matrix as well. If I get rid of the 2, the entries associated with that -2 that got sign changed, that's the first row and the second column. The first row and the second column are going to go away. And that's going to give me this 2 by 2 matrix, what, 5, -4, -1, 7. Okay? 5, -4, -1, 7. Okay. And lastly, I'm going to get rid of, for the 1, I'm going to get rid of the 1, first row and the third column. First row and the third column. What's that going to leave me with, guys? Five, 1, -1, 2. Good, you're right along with me. Okay, guys. And now let's just do the calculation. Let's do the calculation. This is going to be equal to 3 times the determinant of 1, negative 4, 2, 7. And the 2 by 2s you should be able to do in your head. They take a little bit more time, but yeah. Okay? So here's how I calculate this. I multiply 7. 1 times 7 is 7. And immediately say minus. 7 minus, what's the product? What's the product coming backwards? What's the product coming backwards? The product coming backwards, what's that? Negative 8. That's right, Jada. So I say 7 minus negative 8. 7 plus 8, 15. There you go. Plus 2, same way. 35 minus. 35 minus positive 4. 35 minus 4, 31. And don't feel bad if you need to use a calculator for this stuff. It's more important to get the numbers right than to prove that you can do it on your head. Okay? Plus 1 times, again, 10 minus negative 1. 10 minus negative 1, 10 plus 1, 11. Okay? What is this number? And you can use a calculator for that if you like. That's right. Okay? So I get what? 45 and 62, 107, plus 11, 118. Is that what you guys get? Yeah. I know Winter's doing this calculation on the side. Yeah. Oh yeah, guys. Yeah. Yeah, we're going to be remote forever. I gave out calculators. My gift to you. You never have to return those to me. Ain't going to affect my retirement. So, use them in peace. My only regret is now I've got a bag of calculators and I can't give them to students. You're welcome, guys. You're welcome. Yeah. Like I said, $8 on eBay for like a classroom of students is not going to make a difference for me. All right, so 118. That's what happened when we expanded off of row 1. I'm going to do that again, but this time I'm going to expand off of column 2. Okay, so now for column 2, the entries are negative 2, 1, 2. Negative 2, 1, 2 in here, okay? I'm going to change the sign here and get myself ready to expand. So this could give me 2 plus 1 minus 2. Okay? And now all I got to do is fill in the 2 by 2s. So when I came off the first 2, this 2, I actually did that before. It's 5, negative 4, negative 1, 7. And people who are sharp can start doing those determinants already. I'm just going to fill in the rest of the calculation first. Okay. And 1 leaves me with just the corners. 3, 1, negative 1, 7. 3, 1, negative 1, 7. Okay? And now, the negative 2, that was the 2 here. Going to kill its row, its column. Its row, its column. That's going to give me 3, 1, 5, negative 4. 3, 1, 5, negative 4. And now we're ready to rock and roll on that. This is going to be 2 times 35 minus 4. 31. We did that before. Plus 1 times 21 minus negative 1 is 22. minus 2 times negative 12 minus 5 is negative 17. And when I do that calculation, I get 62 plus 22, 84, plus 34, bing. And people doing this in practice, this is what you actually do. You'll expand off of one row and one column. You can pick whichever one and make sure you get the same amount. This is how you double check a determinant calculation. You expand off of one row and then another row, or one row and then the column, and make sure the answers check out. So now I've done that, I've got the determinant. Now, I'm going to get rid of some of this extraneous stuff because you saw that checkerboard and you'll see it again. Because I want to talk about this just a little bit more. Okay, let me fix that, what I ended up erasing. That was a 5. Negative. That's 4. And that's the edge of my matrix, which always looks ugly if I try to stretch it together. There we go. Okay, guys, you saw a bit of how I calculate it. Now here's how I want you to think about it, aside from when you're calculating it. The determinant is called the invariant. It's called an invariant of matrix, and it's invariant under a lot of things. Okay, because what it is really, when you're thinking about it, when you're actually doing the theory on this, my tablet is. Oh, my tablet doesn't think I've got charge. That's okay. I can put my finger for right now. Okay, let's go. What the determinant is, it's a measure of all the product, all the ways you through this. Now imagine you're coming from top to bottom or from left to right through this matrix. With this rule in mind, you can never hit the same row and column or column twice. So once I've hit that 3, I can go to the negative 4 or the 1. If I go to the 3 or the negative 4, my only choice back 2. Got that? If I started at the 1 here, I can go to the 5 or the 1. If I go to the and then the 5, I can only go to the 2. If I go to the 1 and the 1, I can only go to the negative 1. How many products do we get? I got 3 choices of where I can start coming through. Once I choose one of these 3 choices, I'll only have 2 choices left in the next row and 1 choice in the bottom row. And so what I'm looking at is all possible products coming down. It's the same number if I look at all the products right, following the same rule. Okay? Because there's only so many ways I can get a product of these things, one from one row or column as I'm coming through. Now the only difference is those 6 products, half of them I'm going to add and half of them I'm going to subtract. And I add or subtract them depending on the rule, because normally I want to do the product just along this diagonal. And the rule is, what do I have to do to get that particular entry that I'm starting with over to the 1, 1 position? How many swaps do I have to do? Well, negative 4 up here, I have to go 1, 2, 3 swaps, and that's going to be a negative thing. And that there is why this one was included in the checkerboard with a sign change. So you see all the ways that you can run through the matrix. 3 times 1 times 7. 3 times 2 times negative 4. Negative 1 times negative 2 times negative 4. Negative 1 times 1 times 1. All those possible products. There's going to be 12 of them. No, I'm sorry, 6 of them. And we're going to add 3 and subtract 3. Now, the number of ways goes up like a factorial, right? The 2 by 2s, if it was just a 2 by 2, if it was just a 2 by 2, I'd only have 2 ways to run through it. 1, 2, that's it.
And that's why you get that real simple AD minus BC form. One coming positive, and the other one, because I got to swap to bring it over, is negative. Okay? And that's what you're seeing. When it's a 4 by 4 case, now it's 4 times 3 times 2 times 1. Joanne, I got you on pickups today. If you got a problem with transportation, let me know, and I'll show what else I can do. So, but I got you on the list for lab pickups today. Okay? And I got one other student that is be in there too. I got that email from Nikki. So there was another one right there. I jumped real fast to get you guys' names. My students get there first. I know that's me. I should think of all the students for MDC. The fact is, mine are more important to me than everyone else. That's just what it is. Okay. All right. That's how we calculate. That's okay, Jen. It's important that you get your lap today. They're going to be just sitting laptops today. Did you get an email already? You should be getting an email because I got you on the list yesterday. A distribution today. Okay? So, don't have to answer me or anything like that. That's okay. But that's like really important to me. I've got 2 students. You're one that I got in the laptops. And that's like a total of 4 of my students with laptops. Okay. And I like the way that they were like telling themselves how they did it, as if that wasn't always going to happen. Okay, so that was the answer on this. And again, we're looking at these determinants because we want to calculate the inverse. Okay, so let's talk about calculating the inverse. Now, I'll just tell you the truth. I'm going to show you the method of cofactors. That's what CF stands for. It stands for cofactor. But the method of cofactors is really nice and clean. In practice, you would actually use a kind of Gaussian elimination off of an expanded matrix because that's less calculations for the big ones. But this one right there, this is really nice with a theory showing you the cofactors, and it's about the same difficulty as the expansion. It's actually faster. It's slightly faster on the calculations using cofactors than the other methods you would have worked with using Gaussian elimination to get to the inverse matrix that way. And this is kind of nice. Okay, so let's start off with the matrix we were just looking at. 3, negative 2, 1, 5, 1, negative 4, 1, negative 1, 2, 7. Okay? Now the first thing that you're going to do is we're going to calculate the minors. We were just calculating minors. Okay? Now you see a bunch of steps here. We're going to have to go from the original matrix A to this called matrix of minors, M. So there's 9 calculations in there. And then we have to calculate a cofactor matrix. And then we have to calculate the transpose of that matrix. Of these steps, this is the only one that's hard. This is the only one that's hard. It's calculating the minors is the only thing that's tough. But you know how to do that now. The minors are exactly the things we were just looking at for the determinant. So on this one, the 1, 1 minor is going to be given by the determinant of this reduced matrix. 1, negative 4. Man, what's going on with my pencil today? Oh, it was kind of coming unloose. That helps. Okay. And let me lock that down. There we go. 1, negative 4, 2, 7. And I'll want, it's not the 2 by 2 matrix. The minor is not the 2 by 2 matrix. And minor, by the way, is spelled M-I-N-O-R, right? As in too young to drink. Unlike coal miner's daughter, which means too broke to drink, I guess. ask Dolly Parton. She was a coal miner's daughter, right? Okay. Anyway, M11 is what happens when you eliminate the first row in the first column and now take the determinant. So M11, and I'm also going to want M12, which is going to come from the first row, second column. Get rid of the first row, second column. I see 5, -4, -1, 7. Okay, then M13. Get rid of the first row, third column. I see 5, 1, -1, 2. 5, 1, -1, 2. And that's just the same thing we were just doing in calculating determinants. As a matter of fact, we can pull the cofactors out we can pull the determinant off of this in a natural way. Just kicked up my air conditioner. Okay. And now I'm just going to go ahead and write the rest of these minors, and then we'll plug them in. Okay. Whoops. I left my matrix out. There we go. M21. M22. M23. And this is the, they say the first step is a doozy, but this is the only tough step. M31. Third row, second column. Third row, third column. Okay, so let's fill them in. 2, 1. Get rid of the second row, first column. -2, 1, 2, 7. And more neatly. There we go. Most important thing with matrices is writing neatly. In nice horizontal rows and nice vertical columns. Okay? 2, 2. Get rid of second row. Second column leaves me the corners. 3, 1, -1, 7. Okay? 2, 3. Second row, third column leaves me with 3, -2, -1, 2. 3, -2, -1, 2. Second row, third column. 3, -2. Nobody caught that. That's good. 3, -2, -1, 2. Okay. Third row, first column. Leaves me with -2, 1, 1, -4. Okay? And now 2, 3, 2. Get rid of the third row, second column, 3, 1, 5, -4. And then the third row, third column. Third row, third column leaves me with that 3, -2, 5, 1. Okay. And so these are the 9 determinants that you have to start with to use the cofactor matrix. And this is the toughest thing. This is the toughest thing. With a little bit of practice, you can actually do these in your head. Okay, so let me go ahead and start filling in these entries. Okay, for the 1, 1 entry, I'm going to do this in my head. As 7 minus -8 is 15. Okay, or you can do it just coming up with let me frame this as big as I can for your screen. Okay, there we go. Now, I'm going to look at the 1, 2 entry. This entry here, which you're looking down here, but I'm looking over here. I get rid of the first row, and the second column, and let's see, 35 minus positive 4 is 31. Okay? And now the 1, 3, the 1, 3, first row, third column minor. First row, third column, I see 10 minus negative 1 is 11. Okay? Next. All right? I want the second row, first column. Second row, first column. And so what I have left over when I kill that is down there, you see it. I'm zoomed in, I can't do it. Yeah, down here. Huh? Okay. And now I'm going to continue the calculations so we can kind of be done today. Okay. Only got so much time. But this is the toughest thing. Okay. Draw. So, second row, first column, negative 14 minus 2. Second row, second column, 21 minus negative 1 is 22. Second row, third column. Second row, third column. 6 minus 2 is 4. Third row, first column. 8 minus 1 is 7. Third row, second column. Negative 12 minus 5, negative 12 minus 5, negative 17. Third row, third column. 3 minus negative 10 is 13. And yes, that is my original 2x2 matrix. That's the toughest thing, guys. The only difference between the matrix of minors that we have here and the cofactor matrix is changing signs on the chart. It's the same matrix as you just calculated, but now with the sign changes. And with the sign changes, we could take dot products of the original matrix, row with row, column with column. If they match, you will get the determinant, and if they don't match, you'll get 0. That's the really cool thing on this. Okay. So now, let me enter this as 15. Change some. Thought I was in green still. 15. Now negative 31, 11, 16, 22, negative 4, 7, 17, 13. And yeah, you can get that from the 2x2s that I did separately. That's not a problem. But there's your cofactor matrix. And we are like so close. All that's left now, see, here's the thing. If I take a row of my original matrix and dot product with a row of my cofactor matrix, I'll get the determinant. If it's the same row, if they're different rows, I'll get 0. Let me show you one example on that. 3, negative 2, 1. That's the first row on matrix A. 7, 17, 13 is the third row on the cofactor matrix. The dot product is 21 minus 34 plus 13. 0. If I take the dot product of the original, that's exactly what we had just a minute ago when we were calculating when we expanded off of row 1, right? We got 3, negative 2, 1, and 15, negative 13, 11. Okay. 3, negative 2, changing sign, 1, 15, 31, 11. Okay, that's exactly how we had it. And so that's the thing that makes this work. But as far as you're concerned, it's just a calculation. And now, the thing is, when we do matrix multiplication, because I'm looking for an inverse matrix, that's an inverse under multiplication. You don't dot product row with row, you dot product row with column. And right now, I've got the determinant coming out if I take row dot row, and I want it to be row dot column, and so I'm going to turn that first row into a column. That process of turning rows into columns is called a transpose. That's what the T is standing for. This is called the transpose matrix. Lock it down. So what's the first row, guys? What's the first row? 15, negative 31, 11. Everybody sees that, I hope? The first row is 15, negative 31, 11. And what I'm going to do is I'm going to take those entries, 15, negative 31, 11, and I'm going to take that first row and make it a first column. And I'm going to do the same thing for the second row. Everybody sees the second row, right? 16, 22, negative 4. Make it the second column. Okay? And the third row, 7, 17, 13. And that is going to be my transpose, CF transpose. So everybody see this numbers, okay? I need you to write down, at least on your notes for a moment, this transpose matrix. That transpose matrix, guys. Write the 15, 16, 7, negative 31, 22, 17, 11, negative 4, 13. I need to do that because I'm going to change the window in a second. I want you to see something. Okay? I'll give you another moment or two here just to write down this transpose matrix, the cofactor transpose matrix. Okay? And now I'm going to move over to another screen, to another tab. This is Wolframalpha. Oops. Wrong one. There we go. That's my original matrix. Okay. I want you to see some of the basic things that this calculates. This is Wolframalpha. And this is how you enter the matrix, with curly braces and commas and all kinds of stuff. Okay? But here we are. There's the matrix. Don't worry about the plot. It tells you the dimensions. And you can see the trace, right? 3 plus 1 plus 7. They calculate that. And they look at the determinant, too. And we calculated that. It was 118. Now, that transpose matrix, do you see that? That 15, 6, 16, 7, negative 31, 22, 17, 11, negative 4, 13. That's listed as the inverse as soon as we divide by the determinant. As soon as we divide by the determinant. This one's got a characteristic polynomial, but it's tougher to calculate. And there's going to be eigenvalues and eigenvectors associated with that, and they help you get to diagonalization, but you don't have to worry about that until you get to learning linear algebra. Okay? But this has pretty much everything on Wolframalpha that you really need to know, and you can use this to check your calculations. But for me, when you turn things in, you got to show all your calculations so that I can see what you did, so I can give you credit for it, as if you learned it, right? Okay. So now we're going to use this to solve a system of equations. All right? And I'm going to do this with a cheat. Get myself back now to Air Sketch. There we are. Okay, it showed up. So this is the matrix equation associated with the system of equations 3x minus 2y plus z equals something. And 5x plus y minus 4z. And negative x plus 2y plus 7z equals something. And the idea here is that I'm going to want to solve for x, y, and z on this. Now, you've seen professors, they managed to get this done. Okay, I'm waiting for my chat to open up so I can see what people said. No, I'm not saying you have to use it. I'm saying that you can use it to double check your answers. Okay? Yeah. And I was doing it to make you guys, happy that my calculation was the same as was correct. Okay, so everything we did became correct because there's a famous website that says those are the right answers. Now you've seen professors give you these things, you get whole number answers, and my God, how do they do that? Well, they do that by picking the solution first and then writing the B thing. This equation is presently in the form AX equals B. Now you see the cheat here I done? I've used X to be this column vector, X, Y, Z. Everyone does this. It's better if you actually write bar, bar for vectors. Nobody does that because it's just awkward. And you know by the context that we know when I'm writing a matrix vector AX, I mean A times X, Y, Z. Or if it was bigger, we call it X1, X2, X3, X4, X5, however long the particular vector is. Okay, so here we go. I am going to pick a solution. X is -1, Y is -2, Z is 2, and I'm going to calculate those stars. The dot product for my chosen solution, 3 minus 4 plus 2. 5 minus 2 minus 8. -1 minus 4 plus 14. There we go. And what are those numbers? That's -1, right? 5 minus 4, that's +1. Yeah? That's not right. What's going on? That's +4, isn't it? Okay, so there we go. That's +4. And so that number's 9. 5 minus 2 minus 8, that's 5 minus 10, that's -5, isn't it? And that's 14 minus 5, that's 9 again. Okay, so here's how the cheat went. Professor provides you with an answer 9, -5, 9. And asks you to solve that thing. Okay? And yeah, that comes back to the system of equations 9, negative 5, 9. Okay, and now I'm going to let the Wizard of Oz go back behind the curtain so you don't see him. We know what the answer is going to be. Okay? Now let's prove it, and we're going to do it using the standard way. To solve this for x, I'm going to multiply b by the inverse. Let me write that down here. Freeze the screen. If ax is equal to b, then the theory says that a inverse times ax is equal to a inverse times b. So x is a inverse times b. And this is the one thing I want you to take out of this whole module. Yeah, I want you to be able to do partial fractions. But the most important thing to take out of the module is that x, y, z, or xy, if I was just doing that, is going to be a inverse. What was a inverse? 1 over the determinant, 118, times those numbers that we just filled in, that I asked you guys to set up to write on the side. Yeah? Times the numbers I asked you to write on the side. Remember that? And those numbers were 15, 16, 7, negative 31, 22, 17, 11, negative 4, 13. And this is going to multiply by b. 9, negative 5, 9. Okay? And this is equivalent as close as you can get to division. This is as close as you can get to division using matrices. Because you can't divide matrices, it doesn't make sense. What you can do, though, is you can multiply by the inverse. And that's what we're going to do. Now, I could multiply this out myself. Okay? I could multiply this out myself, but we got about 10 minutes left, and I've got a calculator. And so I'm going to let my calculator do my working for me here, okay? Because we've done this going to be dot products. We're going to have dot products all the way along, right? We're going to take, what's going to happen, we have the dot product times row dot column, then divide by 118. So I'm going to multiply this out. Okay? Curly, curly. And I'm going to let you watch me enter it, okay? Okay, so I'm going to enter these matrices. I'm going to divide by 18 when I'm done, but that's okay. 15, comma, 16, comma, 7, curly, comma, curly. Negative 31, comma, 22, comma, 17, uncurly, comma, curly. 11, comma, negative 4, comma, 13, uncurly, uncurly. And I'm going to make sure that I have the right matrix here. Okay, there we go. Right. And then I'm going to divide by 118. There we go. There's the inverse matrix, guys. And now I'm going to multiply it by that B. Curly, curly, 9. Uncurly, comma, curly. -5. Uncurly, comma, curly. 9. Uncurly, uncurly. And there's the result. This is A inverse times B, and the result is 1, -2, 2, which is the exact same answer, we had before I put the curtain back in. Okay? And so we calculate that out, either longhand as an exercise in matrix multiplication or not, and we ended up with what? It was 1, -2, 2. And that is your solution for x, y, z. And got it just by doing it. So as far as the exam is concerned, to solve this, I will end up, the exam I'll be tossing in Friday, I'll give you inverse matrices. I will give you the, I'm not going to force you to calculate the 3 by 3. I'm not going to force you to do the 3 by 3. I will force you to do 2 2s though. Okay? And for that, let's talk about this. Now, the 2 by 2, you can actually write down the answers. It's a really simple idea. What's going to happen here is we're going to WAP along the principal diagonal. And then on the other diagonal, we're not going to WAP those, but we're going to change their signs. So this will become 1, 3, and then it'll become 2, -5. That's how that works. But with that in mind, it's going to have to divide by the determinant again. And then here's 13. We did this. I'm going to do this as if I was naive. Okay. Now the minors, the 2 by 2 are wicked easy to calculate, guys. For the 1, 1 entry, kill the first row of the first column. What do you get? Kill the first row in the first column. Some tell me. Type in the box, please. Kill the first row of the first column. What's left over? People here? Eliminate the first row of the first column. What's left over? Eliminate the first row. Eliminate the first column. Just we were doing minors. We did this 3 by 3's got 2. Now we're going to do yes. That's right, Winter. That's right. I get first row, first column. I've got a 5. Okay. Now, first row, second column. Get the first row, and how many guys? No wonder you're confused. First row, first. What's left over? That's better? What's left over? 1, yeah. 1 is left, and that goes in the 1, 1 entry. Now get rid of the first row, second column. There's the 5. Now get rid of the second row, first column. What's left over? -2. Now get rid of the second row, second column. And you'll see what's left over is just the 3. Pretty simple, huh? You notice already that the 1 and the 3 that I told you were going to swap along that principal diagonal, they've just swapped. And we've got the minors and that's the toughest thing, okay? Now this one, the checkerboard where we had like this entry and this entry are going to have to change sign. Okay, so I'm going to change the sign on those two entries to get the cofactor matrix. 1, 1, -5, 2, 3. Okay? And now the last step is to write the rows as columns. No, not simple. It comes with practice. The only thing that was actually difficult in this process, because I mean, all I did with that last step, I just changed signs in these checkerboard entries. I changed the signs in these checkerboard entries. Before on the 3x3, we had these extra entries, but it just reduces in the 2x2. Just like that. And those are the ones that are going to change sign. Whoa. There we go. And now we're ready to write down the transpose. For the transpose, I'm going to take this first row and I'm going to draw it as a column. So instead of writing a row 1, -5, I'm going to draw the column 1, -5. Instead of the row 2, 3, I'm going to write the column 2, 3. And this means my inverse, because before I know that A had an inverse, had a determinant of, because A has a determinant of 13, we calculated that earlier. My inverse matrix is going to be 1, 2, -5, 3 over 13. That's dividing all the entries by 13. And I can use that to solve a 2x2. But I have 57 seconds left. And so for the 57 seconds left, I'm going to show you how to find the determinant on your general ABCD matrix. And so for this, again, I'm going to kill the first row, first column, and find myself, first row, first column, I find myself with a D in the 1, 1 position. Kill the first row, second column, and I'll find myself with a C. Kill the second row, first column, I'll find myself with a B. Kill the second row, second column, I'll find myself with an A. And from there, it's really easy. You change sign on the checkerboards. And then transpose. And what we see is that A and D have swapped places, and B and C have changed sign. And the only difference between that and the inverse is I need to divide by the transpose. And so what that means, the inverse matrix for any matrix ABCD is 1 over AD minus BC, that's the determinant, times the principal entry swapped and the other diagonal with sign change. Okay. This right there, you have to do the calculations to make it work. But other than that, we're okay. I think I'm out of time, like 1 minute and 25 seconds. Let me review the things we looked at today. We looked at matrix multiplication using the dot product. And that's pretty easy. It's just row dot column. And we practice again finding rows and finding entries. We found determinants, and we did determinants by expansion on a row or a column. And then I found an application problem that you're not responsible. You're not responsible for traces or characteristic polynomials. But I used that as an application for adding and taking scalar multiples of matrices. That's good for linear combinations. And then we talked about inverse and identity matrices by noticing that we could find an inverse matrix and noticing just the basic form of the identity matrix. And then we did the AX equals B turns into X equals A inverse B. This right here is the most important thing from the entire lecture today. Find the inverse matrix however you find it, whether you got to calculate it yourself or I give it to you. You'll still be able to use this to calculate X from this. And we did a little bit more theory past that, right? I showed you how to add, subtract matrices and multiply them by themselves. Then I showed you how to calculate determinants by expansion of a row or a column. Then I showed you this method of finding the inverses, and this one I know is a little bit tough on the 3x3. When you get to 4x4, it's really crazy. 5x5, oh my God. You have to do that for your master's exam if you want a master's in math. And then you get to do more stuff. But there are things to make it easier. And then we solved a system of equations using the inverse matrix method. And then showed you how that applied to 2x2s. But for the 2x2s, we actually have a formula. We end up with an actual formula for the inverse matrix on a 2x2. Okay? And that one's so easy you should just know it. It's a swap along the one diagonal and a change sign in the others. Okay? And you'll be asked to do a couple of those on the thing on Friday. Okay, I'm going to have, because I promised, I'm going to have an office session coming immediately after this over in the course room, which is always open. Okay, guys? Why is this thing showing I've got one chat that I didn't see? It can't see. It's just like, what? How can it have a chat that I didn't see? Oh, I know. That was the private chat. Because I never clicked in that. I just saw it. Okay. All right, guys. So there we are. Thank you guys for all your attention today. Joanne, make sure that you get your laptop or let somebody know if you need issues getting out there, okay? For the rest of you guys, you're gonna have the new. I'm going to again. You got 6 o'clock. 6 o'clock. I'm gonna bring, and it's just anybody doesn't have anything in there. It has no submission right there. You know, I don't know. You're not gonna be on the path for passing the class. That's all I can say. I've done as much as I can on that, and I gotta work with the students who are gonna pass now. Okay, so that's how this is gonna work. I'll get those things back to you sometime this weekend. And on Friday, you're going to get a new exam for you guys to work with, okay? And the rest of you guys are going to get the stuff over the weekend with a revision exam for and you'll do sections on that one. Any sections that you didn't have right, you'll have to redo. That's how it'll work, okay? Take care, guys. Have a great day. Enjoy the rest of your week and your weekend. Stay safe. And remember that everyone should be asking as you go by, who was that masked woman? Bye. Bye, guys. Notes go up, up, saved files, IMDC 2019 spring, go to sorry, leave, leave,
I can use this mic here now because I left the session. Yeah, Joe, I'm going to be moving over to the course room now because I need to close off this session. Okay? Thanks for stopping by, Shair. Okay? And I'm going to kick you out now, Jewel, and we're going to meet you back over in the course room. Oh, you're all good. Oh, that's cool.